Mathematics seminar at Rutgers University. I'm very welcome to the new students. It's nice to see new faces. In case you don't know, there are certain axioms in this seminar. The first one is the time limit. It's 48 minutes ideally, but at most 50 minutes. So it's only 50 minutes. Unlike some talks that go over time, you never know. This talk, every talk here is guaranteed to be at most 50 minutes. Hence, it's not unreasonable to expect people not to use any electronic devices, smartphones, cell phones, laptops. That's an axiom. This talk is an exception. Usually I never repeat the same talk twice. But this talk I already gave in Beijing in a conference, in the part of the International Conference on Applied Mathematics. Because there was a tiny blackboard. So it was all verbal except for one formula. So I got a little bit frustrated. Also, here is going to be videotaped and be recorded for posterity. Also, 25 years is the official duration, really 25 and a half years of WZ theory. It all happened in Christmas Eve of 1989. My late good friend, Herr Wilf, called me up and he read my paper and he's found a way to simplify into one line my computer-generated proofs. So let me give you an example of a few WZ-generated proofs that are completely one-liners. Identities that before took smart people, Gauss, Euler, and many, many others, Dixon, to name a few. And every time they had to work several days or several months to get a proof, and then sometimes people found better proofs, could be done in one line. So let me give you a few examples of WZ-style proofs. I just use my computer. So now if you go to Maple, also Mathematica, but Maple is better, you go to a package to do with, or like this, in Maple, sum tools. So here's a command that in one line solves many, many identities. Gauss, Euler, Kummer, all these big people, and also not so famous, Dixon, Vandermonde, Dougal, in one line proves the following command. So that's went to Maple before. Sum tools. This is a package. It's an open bracket. Hypergeometric. I explain what it is in due course. So it is certain. And then open bracket Zeilberger. And then here's the argument. Here's the proof of the binomial theorem. Or really in humanese, the special case of the binomial theorem. That in the so-called Pascal triangle, that it really goes back to Chu in China, the sum is to the power n. So what you do is divide the right-hand side. This is a beautiful, beautiful observation that in hindsight seems trivial, but it's brilliant of Herr Wilf. So you have an identity, blah, 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 equals right-hand side. Step number one, divide the right-hand side and make the right-hand side 1. And then you enter here in Maple notation, binomial, open parentheses, n choose k, divided by 2 to the power n, comma, n is for the parameter, k is for the summation index, and then a symbol for the so-called shift operator. The shift operator is really, if you have any sequence, you go to more. So f of n is what happened to more. That's a fundamental shift operator. And you can make up your own. And in maple, everything ends with a semicolon. And in 1 fraction of a second, you get the answer. Capital N minus 1. And here you get some function of k. Oh, hi, welcome. Welcome, thanks for coming. Sorry. What happened was very embarrassing. In my original talk in China, I declared very loudly, no smartphones, no electronic devices, but then some people came 3 minutes late. And the first thing he did, open his laptop. So I have to repeat every time. So thanks for coming, but no laptops and no smartphones. Okay, thanks. So I hope, anyway. So, and here, I'm copying it, K. So that's the output after 1 nanosecond. And I explain what it means. It's really the complete proof. Divided by 2n minus 2k plus 2 to the power n minus 2. This is the proof. What it's saying here, this is a shorthand that if you divide, if you call this A of little n, so forget about the right hand side. Let this be a sequence. For every integer n, let this be the sequence. Then this output is shorthand for the fact that A of n plus 1 minus A of n equals 0. This is just shorthand for this. So it tells you, so this sequence defined according to this satisfies this recurrence relation. Then it's left to the reader to prove the base case. A of 0 is 1, because sigma k goes from 0 to 0, of 0 to k, over 2 to the power 0, k goes from 0 to 0. It's, even math you can do it. What is it? 1. Right. So you know that A0 is 1. But another way of saying, so A of 1 is 1, because A of 1 equals A of 0 equals 1, and hence A of 2, A of 3, and by induction, it's true for every n. So A of n. So this is a theorem for every n. And if you think that this is trivial, you can do many, many other things. Instead of this, if you go to the website of the undergrad math major at Rutgers, you have the following. The following icon or logo. That's it. Here. So here, so let me just transcribe it. So in 1 second, but this I explain in a second. This is the statement. This is the proof. I tell you in a second. But right now, let me just give a few more examples. So the one in this famous T-shirt that you can just go. If you had your laptop with you, you would have been able to verify it, but you have to wait 45 minutes until you can verify it. Go to the website. This T-shirt was made by Herr Wilf's son, David, who is a very smart person, but he's not a mathematician, he's a lawyer. So Herr apologize. So that's a nice T-shirt, but not exactly what a mathematician would do. And then who are you going to call? I guess it's a reference to Ghostbusters, as my daughters told me. So 3n plus k, so this is something that looks much more complicated than the monomer theorem. Lo and behold, this complicated sum also has a nice closed form. 3n should n. So once again, the same old trick. Divide the right hand side. And do copy and paste this, write it in table notation, and then you get something else, much more complicated, but for the computer, it's no big deal. And you always get this, and let's call it, in general, this is called the certificate. This certificate embodies the proof. So what it's saying is that whatever the computer spits out here has the following property, that it forms the second part of a so-called WZ here. So if you call, so every explicit identity, and there are many others. Another one is right here. This research was done by Sarah Bailey when she taught the course at MIT in 2002. The so-called Dixon identity. And let me put it here. Dixon. Also, there are many. I know at least 5 proofs. All of them nice but complicated. So it's A plus B choose A plus K times A plus C plus C choose K times B plus C, and B choose B plus K minus 1 to the K. Lo and behold, it's a trinomial coefficient. So here are 3 parameters, A, B, and C, but this works out as well. So here's another example. So that's the t-shirt here. And Dixon's identity, 1903. So here it is, and here's the proof. So let's do it here. And so in this case, you just copy blah blah blah, but now instead of K, it's A instead of N. Okay. So lo and behold, so the first step, make this 1 by dividing both sides. And then make a convention that is from negative infinity to infinity. Of course, it's only a way of speech, because the binomial coefficients are 0 when K is negative and when K is bigger than N. So it's convenient to make the nature of summation. So this is what you have to prove. And lo and behold, the computer, this command, gives you the so-called mate, WZ mate. And together, F, G is a WZ pair. And it's a beautiful property that the computer in 1 nanosecond, usually, unless it's very complicated, of course, come up. So the output of the command here, first, it always says, if it's true, usually, always. There's some cases where it's still provable, but not. But usually, you get this, and then this. Now, what if you don't believe in Maple? So this is called also the certificate. Together, it's a WZ pair, and this is called, ZLK is called the proof certificate. Because it certifies, it certifies the identity. Why? So, if you don't believe it, you can go ahead and check it. This is completely routine. You can use a calculator to do it numerically. You can also divide both sides by f of nk. Sorry. I'm messing up. F of n plus 1k minus f of nk. Sorry. Or in more abbreviated says the delta sub n. The difference with respect to n, the forward difference. So that's the formal definition of the famous WZ pair. So this was Herr Wilf's great observation that you can make it into one-liners. But this by itself is nice, but it was amazing consequences that came up later. So first, why does it prove it? So once you came up, when the computer came up with this magical G and K, the proof is immediate. You apply sigma to both sides. Okay, from negative infinity to infinity. Now this has a beautiful property. It's telescopes. D of n of 1,000, and this, so it's a telescope sum. Summation respect to k. So this is automatically 0. So hence, defining a of n, this is a of n, this is n plus 1, you lo and behold, get this recurrence, very simple recurrence, that proves in one stroke this. And this can be applied to anything, all these people. Look at the classical books by Bailey, a collection of 100 different identities, all of them with different ad hoc proofs. Can be done in one stroke. So that's an example of an algorithmic proof theory. Something that could be completely mechanized without even any human source. But it's not the first algorithmic proof theories. There were lots of algorithmic proof theories before. One of them is discovered 5,000 years ago. Addition. To prove the identity, 2 plus 3 equals 1 plus 4. You don't have to think very much. There is an algorithm. You convert 2 to unary. So the cave person puts 2 strokes. Then you convert this, and then, and you count, yeah! So that's an example of algorithmic proof theory. And then later on, things became more efficient. You can express this in binary or decimal notation and make it faster, but nevertheless, that's algorithmic proof theory. So this was no longer considered mathematics, this became accounting. But then came very advanced things and apparently needed human ingenuity. For example, the following general fact. For any integer n plus 1 squared is n squared plus 2n plus 1. For every n. And in the old days, it required a human proof. And still, now we torture people like this. You use a distributive, commutative, blah, blah, blah. So you open up by distributive n squared plus n and 1. But now it's algorithmic, complete algorithmic. It's high school algebra. And now everybody knows that high school algebra is completely algorithmic. You don't have to be smart. You can do it completely mechanical. You can use Maple or Mathematica or Sage, anything. Another class of theorems, and this is still amazing. I'm so amazed. In geometry, plane geometry. 300 years ago, a very smart philosopher who was also dabbling in mathematics called René Descartes found a way of translating geometry to algebra. Every geometrical statement in 2 dimensions could be translated into a high school algebra thing. So there is a way. At the time we didn't have Maple Mathematica, so sometimes it was still more fun to do so-called synthetic proofs using the Euclidean approach. But in principle, you didn't need Euclid. You can just do everything in terms of high school algebra. And then, but you didn't have computers. But now we have computers. So one of the famous theorems, and I'm really, really amazed. So there is an algorithmic proof theory for plane geometry. If you go to my homepage, there is Shalosh Diachaj Geometry webbook. So I have a Maple package. So it's really an elementary textbook for the year 2050. So it was completely, all the statements are computerized and provable. All these famous theorems in geometry, and one of the about 60 theorems there is the famous Morley theorem. So let me remind you, so I'm talking about another algorithmic proof theory. That is not, people are not aware that this is really completely routinely provable. As you know from 8th grade, that if you take the bisectors of a triangle, they meet at a point. If you do it correctly, it's concavity. But about 100 years ago, Professor Frank Morley, who was teaching at Johns Hopkins, I think, said, what if you transect the angle? So then, if you do it correctly, you always get an equilateral triangle. So the middle triangle here, let's call Morley's theorem. So it's always equilateral. And that's one of the 60 theorems that Zeilberger had proved in 1 nanosecond by transcribing it according to René Descartes to a high school algebra with completely routine. This theorem fascinated many, many people because the Wikipedia page, you have 12 proofs. And some famous people worked pretty hard to do it. And I'm really amazed. One of them just came a good friend of Niels Sloan, Jacob Niels Sloan, and Neil is speaking in 2 weeks in this seminar, don't miss it. And Matthew is speaking next week, don't miss it. But a good friend of Niels Sloan, Conway, is so proud of his proof. And he's so proud in his biography that just came out, that I recommend, it's a very good biography. In the appendix, this is. And frankly, I tried to read it, and Conway claims that it's a beautiful proof. I had to struggle to read it. It's a nice picture with a puzzle, but it took some effort. So John Conway, superstar mathematician, believed he needed to prove it his way to really understand it. And then my former colleague from Temple, the late Don Newman, has another proof that also died as far as human proofs go. And somebody even more famous, Alain Cohn, physics analyst, has a 3.5-page proof doing it this way. Would Alain Cohn and John Conway publish a proof that 11 times 13 equals 143? So it's nice if they get a kick out of it. But I'm not sure whether they're aware that this is a completely routine, computable high school algebra. And for some reason, and maybe one of you will volunteer, in the many proofs in Wikipedia, there's no link to the Shalosh proof. That in my humble opinion, maybe not the most elegant quote unquote, but it's the most straightforward. So let me tell you briefly how it goes. So you call the slope of the transector n. So it's completely routine to find the equation of this and call this m, the slope here. The completely routine using the macros, the thanks to René Descartes, to find the equation of this straight line as a rational function of n, of this straight line as a rational function of m. So you get the location of this, ditto for all the other points that show up. Then another macro distance square using René Descartes' famous distance formula. X1 minus x2 quantity square plus y1 minus y2 quantity square. It's also distance square. And then it's completely routine calculation to show that this side equals this side equals this side QED. So that's an example of an algorithmic proof theory thanks to René Descartes and combined with modern computer algebra system is completely routine. No need to be a physics medalist.
Can you use the routine computation to see what's going on in some of these synthetic proofs?
Oh, that's a good project, but beyond the scope of this talk, but sure. For people, There's another thing, it may inspire human proofs. So that's one example. Another example that is even less well known is Fibonacci identities. There's a whole genre called Fibonacci quarterlies, and still in the monthly, in the most recent monthly, there was a beautiful, quote unquote, I'm being sarcastic, utterly trivial Fibonacci identity. Every identity, even complicated one, in the whole book by Benjamin of insightful Jenny Quinn and Al Benjamin of insightful proofs. And Nathaniel knows how to make it nice computer-generated proofs. But once again, that's another example of algorithmic proof theory. Every identity involving Fibonacci, or more generally, any sequence that satisfies a recurrence is constant coefficient. And the Journal of Integer Sequences, no offense to Neil, but I is not responsible because somebody else is the editor, still publishes. So it's okay to publish insightful quote-unquote proofs of this. But you should be mentioned explicitly. This is purely routine. So in this case, any Fibonacci identity is very easy a priori to come up with capital N and fairly small, so that if you check it for the first capital N values, then it's true rigorously forever after. In analogy, my favorite proof of the identity that I gave you before is not how you learned it in high school, but just plug in n equals 0, n equals 1, n equals 2, n equals 3. Since both sides are polynomial of degree 2, if you check it for 3 special cases, it's a completely rigorous proof. And there are no examples. So that's an example of an ansatz that has an n0 property. So the WZ proof theory is yet another algorithmic proof theory. And no offense to myself and to have Wilf, I think its great significance is not so much for its actual content, but as a role model for future algorithmic proof theories. And my dream is that Andrew or Disco has already proven the Riemann hypothesis. Andrew or Disco computed the first billion zeros. He proved that if this of n is the nth non-trivial zero of the so-called Riemann-Zeller function, the real part is 1/2. And I believe that once the right ansatz will be found, capital N will be probably 100. So probably Andrew Adisky wasted a lot of computer time by verifying it for first billion cases. But this is still yet to be found. But this is just an example of things that is still. So unfortunately I don't have a proof yet. But I believe that sooner or later there'll be one. So now let me give some content back to WZ theory after telling you the great significance of it. The history is very, very, very old. It's not just 25 years. It's at least 5,000 years. Or at least in China, or maybe 2,500 years. There was a philosopher, Zeno, who, like me, was a skeptic. He said you can't believe everything you hear. For example, he tells you he has a paradox, the famous is Achilles and the tortoise, but a better one is the halfway paradox. You never make it from here to here. First you have to go halfway, and then halfway of the quarter way. And wherever you go, you still need to go a little bit more. So you never make it to your destination. But now we know that if you go to infinity, it is 1. So there's an example of a geometric series. So in modern notation, and that's a proof, because we want to go halfway. So that's an example of a geometric series. And with Achilles of a tortoise, Achilles was 100 times faster, was 1,000 times faster than the tortoise. So it is